inter symbol interference. So we introduced this concept some time back, wherein we send the message pulses for a long distance communication, and after some time the energy content of one of the symbol tries to occupy the energy content of the other symbol, causing some interference, right? This is what is called as the inter-symbol interference. All right, so let's look at the mathematics behind the inter-symbol interference. Why this happens is our main idea. Okay, we want to analyze that. So what we do, we'll start with the fundamental baseband transmitter and a receiver. Let us consider that. So whenever we have a communication system, it has the following components. All right, so it starts with an input. Normally this is going to be a binary data including zeros and ones. So always what happens is we try to give this as input to a block. So that block will be called as, say, a pulse generator circuit. So this generates the pulse. All right, then in order to see, when we have the pulses, maybe that pulses as it is may not be capable for the for carrying the data for a required distance, right? So you may require some other circuits to increase the energy content or the power content, etc., right? Also to just to check that whether the content of or the message format is suitable for communication, etc. So to do that, to check that whether it is suitable or not, we will be having another circuit. So the output of the pulse generator, let us denote this as, say, x of t. Okay, so there is this x of t. This is given to another filter, another circuit that's actually called as a transmitting filter. Okay, so this has a transfer function denoted by h t of okay, let's write in the frequency domain, because most of the terms what we already have dealt, they are in the frequency domain, right? So I'll write a frequency notation, the Fourier transform. So that is ht of f. All right, so this is that circuit which performs this. Now you see this will be sent to the channel. So assume that this is connected to the antenna. So the antenna will transmit to the channel which carries the signal. So if it is a free space, definitely this will be air or right, something like a free space. Okay, so what I do, I directly connect this to the channel. Right, so channel is denoted by a transfer function hc of f. So channel has its own property, right? Maybe you have already studied in some part of some of the previous chapters, where right, channel will also affect the communication, right? Some of the channels are frequency selective, they pass only certain frequencies, they drop the some amount of frequency, right? Different types of attenuations are possible, right? Different channel models do exist. That model is represented by this hc of f. Okay, so actually let's try to separate something here. So this part is actually the channel, and these dotted lines separate the channel from transmitter and the receiver. Okay, so let me move on to the receiver side now. Whatever is the output of the channel will be received by a specific filter on the receiver. It is called as the receiving filter. Okay, so receiving filter is used to receive that whatever has been received. Now on the receiver side, the most common part will be a sampler. So that actually samples the output that is coming from this filter. Let us assume this is where the sampling happens. So sampler will sample this at a particular intervals of time. So this is the sampler notation that we use. All right. This is I'll denote the output of this as y of t, right? So sampling happens at every t is equal to tp. We know that because we converted the inputs in the pulse generator. Pulse generator is using a sampling duration that is equal to tp, correct? So I have to sample it back to convert that into the original message signal. So that's why I'm using a sampler over here. So once you sample, you get some output. So let us denote that as, right? So this is y, this is still y, but this is y of some integer times itb. Okay, so I'll write it properly. So this is y of I times, I is an integer, times tb, like 1 into tb, 2 into tb, second time sample, 3 into tb, third sample, and so on. Okay, so we have something that exists over here, which is used to make a decision, right? So because you receive something as y of itb, so whether it is a 0 or 1 needs to be decided by this circuit. So to make a decision, it takes another input that is called as a I'll write this as lambda, which will be the threshold. Okay, right. So there will be a threshold value. Depending on that, it will make a decision. So decision should be, right, what is the binary value? So this output, what comes over here, right? So this value itself is the binary output. So I can write once again output. So that consists of binary. So we started with the binary data at the top on the transmitter side. Again, on the receiver side, it's same thing will continue. So where is the transmitter? This part is the transmitter. Okay, I'll simply write tx. And where is the receiver part? So this whole thing will be the receiver, this side. Right? Okay, in the middle we have a channel. So this is a transmitter receiver system corresponding to whatever pulse we generated in the previous sections. So we use various types of pulses to convert our messages onto the pulses, right? Right. So that system will be, this is the system that is going to be used to transmit that data. Okay, irrespective of what type of PAM signals you generate ultimately. Okay, now let us start with this x of t, which is the pulse, which is in the pulse format. Okay, we are going to start the concept of what is called as ISI with the help of this equation of x of t. Okay, so it's again, it's going to be the mathematical analysis completely. So let the x of t be generated in the, be represented in the following format. We already know this. This is, say, k is equal to minus infinity to plus infinity, some amplitude that is given as ak into a pulse signal, that is normally pulse is g of t, but you know that it is shifted by k times tb, correct? G of t is here, maybe it is shifted to right, g of t minus tb, shifted to further right, t minus 2 tb, shifted to left, plus tb, plus 2 tb, plus 3 tb, and so on, right? So you can see that shifting can happen from minus infinity to plus infinity. All right, so let me call this is equation number 1. So I have to specify what are my variables. So let me write that. So this is where the what is g of t? As I told, it is the rectangular pulse, right? So normally there will be a condition like I always use g of 0 equal to 1. At the center, I have to keep it as 1. Okay, then what is AK? Right, AK is it's a random variable which takes plus a for symbol 1 minus a for 0. Okay, so let's say this is plus a for symbol 1 minus a for symbol 0. Okay, it can be the otherwise also. You can have any other method as well, no issues. And we use another term called TB that represent the bit duration. All right, so we know this. Now let's go to the frequency domain. So in frequency domain, if g of t is what you call the rectangular pulse, so let's write one point. Let the g of t, which is the pulse, has the Fourier representation that is denoted by g of f. Okay, but I don't have g of t as it is in my equation number 1. Instead of that, I have what is called as g of t minus t naught. Right. So what should be its Fourier representation? So there is some property. If you are able to recall the property, please let me know. If g of t has Fourier representation g of f, what is the Fourier representation of g of t minus t naught? There is a property called, right, if what is this? G of t to g of t minus t naught means which operation is that? What you are doing with g of t? No, in terms of time domain, what you are doing, right? If at all I have g of t over here, g of t minus t naught means what? So this was 0. T minus t naught means you are shifting the signal to right by t naught units, isn't it? So I have g of t. This is what happens. G of t minus t naught. Sorry, I think we cannot see. I'll just visible. Okay. So g of t was there. I performed what is called as shifting. So shifting will result in, this is a right shift because t minus t naught, correct? So we use a property called, right, I'll write the property name. It's called as a time shifting property of Fourier representation, specifically Fourier transform. Okay, so that means if you shift in time domain, on a frequency domain, that is right side, you will multiply by a complex exponential. That's what is the property. Complex exponential is e to the power minus j into 2 pi frequency domain, so f, and the shifting constant t naught. Okay, this is a t naught into the g of f. So this is what is called as the time shift property of the Fourier transform. So that is g of t has g of f, g of t minus t naught will have its Fourier representation as e to the minus j 2 pi f t naught into g of f. Okay, that's what is this. Let me call this as equation number 2. So that means, right, if at all I am trying to take the Fourier representation of my first equation. So where is the equation number 1? You can see here. I try to take the Fourier of this, right? So from 1, therefore, taking the Fourier transform of 1. So it was actually x of t. What happens when you take the Fourier representation? It should be represented as a frequency domain term. Let me call it as a x of f. X of f is should be equal to, so you see there is a summation. The summation will remain as it is, k equal to minus infinity to plus infinity, you had a constant term over there. I'll show you the equation once again. You can see this is ak into g of something, right? So ak is a constant. So Fourier representation in that, if you have a linear multiplier, it remains as it is. This is what we have studied in signals and systems. So ak remains as it is. But you can see that there is a g of t minus t naught, which gets replaced by this term. Okay, this term will come over there. So that is ak into, instead of g of t minus t naught, you will write g of f into e to the power, it is minus j 2 pi f. Now you see, it was right f into t naught, but that t naught is not there now because t naught is replaced by k times tb in the equation. Let's go back. You see, there is no t naught, there is ktb, right? So that ktb should come in my equation now, right? In the current scenario. So that means f into, instead of t naught, I'll write k times tb. You understood why? Okay, fine. Let me call this is equation number 3. Right. Now, very similar to this, let's go back to the diagram we wrote just now. So that's the that is this. Let me just go down. Okay, I'm talking about this particular diagram, wherein my intention is to see the equation of y of t. Right. So anyway, I don't know what is the channel's response hc of f, what is the transmitting filter's response, etc. I don't know, right? But we can definitely put some equation and we can write. So it's obvious that x of t in the sense this part, right? So this is made up of what? That is made up of pulses, right? So definitely some pulse will come at this point, right? Output of this filter will be some pulse. Okay, right? That pulse will pass through the channel. Whatever may be the response of the channel will still generate another type of pulse here. Okay, some pulse, maybe pulse amplitude may be attenuated, pulse may be elongated, or something might happen. Okay, but you still get a pulse. Okay, then there is a receiving filter whose output y of t. Now I am trying to write a y of t itself. That is also going to be in some format. It's going to be a pulse because your original signal, what you are sending, is a pulse. Okay, so it will be in the pulse. Anyway, we are not going, since we don't know ht of f, hc of f, or even the receiving filter's response, etc. We don't know, right? So we cannot go for the exact exact equation, right? So we'll do this analogy and we'll write the this thing equation. So let the receiving filter output, right, be denoted by, anyway it's already shown, that is y of t is equal to, again it is made up of pulses, so I have to use k is equal to minus infinity to infinity. It is not a single pulse, it is a shifted pulse, so there has to be a shifting index, right, indicated by the k. Right, now you see, originally I send ak, right, from the receiver, sorry, from the transmitter, my mistake. On the transmitter side I send ak. So there is a channel, right? Definitely channel will do something with its amplitude, correct? As I told, it most of the time the amplitude will get reduced. So there is a scaling factor coming into picture, which is mu into ak. So ak turns out to be mu into ak. Okay, so I'll write mu times ak. Then you used a g of t minus some t naught. You send from this side. Okay, not t naught, it can be t minus ktb. What happens because of the channel? The g becomes some other pulse denoted by p. Okay, p of t minus t naught. That's what. So as I told, you receive some pulse. Let us denote that pulse on the receiver side as p. So you send g, you receive some p. Is it okay? Right. So let me denote that. So mu into ak into, this is the pulse function we represent on the other side, that is still t minus k times tb. It will remain like this. Okay, right, where Anyway, we understood this, so I'll just erase this part. I'll write every term so that you understand when you read it later. Okay, so where, let's write the terms one by one. If I write the P of t somewhere, that means the pulse shaping function is a pulse shaping function of the output, that is y of t, right? So there is a scaling factor mu. You have a scaling factor which brings your amplitude ak to mu into a. All right. Then again, I'll assume one more thing here, like we did earlier. P of 0 should be equal to 1. Other than that, right, the right side or left side of the P, it can be. That's absolutely fine. Okay, right. Now, uh, anyway, AK is known to us, so I don't have to write that. So I had to write what is mu, what is P, we wrote that. Now let us try to look at the Fourier transform of this. I'll call this is equation number 4, right? The y of t. So taking the Fourier transform of equation number 4, right? It is y of t in time domain. It should become y of f. Very similar analysis, right? There is a summation which remains as it is. Whenever you have a summation in time domain, even on the frequency domain, you are going to have linear combination on time domain will remain the same linear combination on the frequency domain because of the property of Fourier transform that is called as the linearity. You might have heard of linearity. So Fourier transform is linear. So k is equal to minus infinity to plus infinity. The mu and ak are constant, so they remain as it is, mu into ak, right? But right, let's assume another point here. I'll write it here. So you have P of t whose Fourier representation is P of f, right? Using the same analogy we used earlier, which implements the time shift property, I can see that P of t minus ktb, right? So whenever I have P of t minus ktb, what should happen? It's a Fourier representation. So P of, if I write t minus t naught, then its Fourier representation has to be the same P of f which you wrote earlier into e to the power minus j 2 pi, right, into the frequency f into the t naught, right? But now I don't have t naught, I have ktb. So when I write in the y of f format, I should replace that as the p of f into e to the power minus j 2 pi f, right, into t naught. T naught is ktb now, so this is k times tb. I hope this is fine, right? Equation number 5. Okay, now let's go back and let's look at the block diagram we wrote earlier. Let me see if I miss something. So we have x of t passes through ht of f, that is a transmitting filter. Then it also passes through the channel denoted by hc of f. Okay, I didn't write the receiving filter. Let me write that. So this is denoted by hr of f, right? Okay, so you see that this is my point. I have x of t. It passes through this filter of response ht. That output passes through another filter of hc, which will once again passes through hr of f to get y of f. Correct? So that's the point, right? Just remember this. I'll write it in the frequency domain format. Okay, just to understand what we did now. So let me write that in the following notation. So there are 3 filters, right? So that means, but from the block diagram, right, the y of f is equal to y of t was written over there, but I'll shift to y of f because In time domain, the calculation is convolution, which is difficult. But if you remember the convolution property of a Fourier representation, time domain, if you have convolution, on the frequency domain, you have multiplication. That's why I am not writing y of t here, I am writing y of f. Y of f is nothing but what is there on the leftmost side is the input signal. Input signal in the frequency domain, it is x of f. X of t means I have to convolve, but I'll move it to x of f so that you don't have to convolve. Simply multiply. Okay. You see, first the x of f, which is the input, passes through the transmitting filter that is denoted by ht of f. So I multiply. So this result passes through the channel denoted by hc of f. This output passes through the receiving filter denoted by hr. Are you okay with this equation? Right? So we time domain convolution got converted directly into the simple multiplication because we took the Fourier representation. That's why we need the Fourier. Okay, that means, right, let me try to substitute the values, right, from all the previous equations. I know what is y of f. From equation 5, I'll write what is y of f. Okay, so from this equation 5, I'm showing you here. So let me write this y of f, that is LHS I substitute, that is summation k is equal to minus infinity to plus infinity. This is mu times ak into the p of f e to the power minus j 2 pi into the frequency f into k times the tb. That is the left hand side directly from equation 5 is equal. On the right hand side, you can see I am substituting only for x of f because the other three equations we are not aware of. Correct? As I already told you, we have assumed that there are filters like this, but we don't know the equation. So we cannot substitute for them. We'll keep those three terms as they are. Only I can substitute the value of x of f because somewhere here we wrote x of f. You see equation 3, right? The equation 3 is x of f. I can substitute. So let me put the x of f over here. That can be substituted as, once again, summation k is equal to minus infinity to plus infinity ak g of f into e to the power minus j 2 pi f k times tb into the h. This is what I'm going to keep as it is. ht of f remains as it is. I'll still substitute the hc of f same into h r of f. Okay, right. So which means I can actually try to eliminate the similar terms on both the sides, right? That means so when I have some same summation on both sides, you can eliminate. Okay, when you have, yeah, both are capital, both are same, you use capital or small, doesn't matter. Okay, so the point here is this. So I can see that this in the color for this thing. So you see this k and this k, you can write one side capital, one side small, doesn't matter. As far as this limit is same, they are going to get cancelled. Okay, so it's the same limit, right? With the summation, you can have m on one side, n on other side, doesn't matter. It will still get cancelled because that satisfies the mathematics, right? Basics of mathematical condition, what you need to cancel the summation get satisfied over here. So you can definitely, yes, cancel. Then I can see that the AK which is here, same AK I got, I can still cancel. E to the power same will get cancelled. Okay, remaining terms I cannot cancel, right? I am going to write them now. So after cancellation, right, this implies what's going to remain? Mu will remain on this side, mu into p of f will remain. right? So this is equal to, on the right side, I am going to retain the g of f h, that is h t of f h c of f into h r of f. So let me call this as equation number, say, 6. Right. Now my intention is that I want to take the inverse Fourier representation. Okay, I don't want to uh, keep it in the frequency domain. I want to come back to the time domain, right? So that I can see what is going to happen to my equation in the time domain. Okay. All right. So, but before I take the inverse Fourier, I would like to look at my equation of y of t, which I have already written. Okay. So I'll write that equation. I'll look at the equation number and I'll come back. So that is equation number 4. Y of t is equal to summation k minus infinity to infinity mu ak p of t minus ktb. Okay. Uh, this is what you get. This is how you get. But from equation 4, I can write this inverse Fourier, right? That is y of t is equal to, let me write the same equation, that is k is equal to minus infinity to plus infinity. You have mu times ak into the p of t minus k times t. This is what you get when you take the inverse of the equation number 6. Okay. So anyway, that's what I'm going to hold now. I'll go back to the diagram, block diagram, because I want to see what I'm going to get at this point, because I had the y of t, which is here. You take a sample and you get the y I of t, correct? So that's where sorry, that y of itb is the one which is used by a decision device or decision making circuit to get your output. That's where error is going to come, right? Because of the ISI, we have not seen the ISI yet, but what we are going to see now is that the decision is going to be wrong if there is ISI. So I have to see what is y of ITB. If there is a mistake, if there is something wrong with the y of ITB, right? That's the reason for wrong decisions, right? So let's try to go with that part now. So let us look at the output of the sampler. This implies the output of sampler circuit at uh, at a t which is equal to I times t, right? uh, where I'll write I will be equal to either 0, you can have plus or minus 1, plus or minus 2, and so on, right? You can have the samples at any point in time, right? So that should be denoted like this, right? Is equal to y of I times tb should be equal to, it still holds the same k from minus infinity to plus infinity, mu to ak into the p. It's still this p, but you see what happened, what is the change? The t has to be replaced by itb. Where is a t? There is a t here. So this tb, when I write in this position, has to be written as itb. That's all. So that's the change, itb minus ktb. ktb is already there. Are you fine? Okay, let's proceed further. So let's try to do some mathematics over here to get it into some form which we understand. As of now, I don't know what is this. Okay, so let's go. Let's proceed further. I can see the TB common inside the bracket of P. So let me try to simplify that. So say this is k is equal to minus infinity to plus infinity. This is mu into ak into the pulse. I'm going to write, okay, I'll use a different bracket so that I need two brackets over there. So this is P of, see the TB is common. When you take TB out, I'm going to have I minus K inside the bracket into TB. Are you okay with this? Okay, now we know something. Already we assume that whatever may be the pulse P, right, it has one characteristic. That is P of 0 is equal to 1. Correct? In the sense, if I write inside the bracket is 0, its amplitude will be 1. That's the central value. At the center of the pulse, it is always going to be 1. Okay? Right. So that's the fundamental characteristic of the pulse. So what I'm assuming is this. So I sent a pulse like this. Okay? On the receiver side, what you get is something like this. At the center, it is still 1. Maybe its shape is changed. Okay, so at this point it is still 1. I sent the same thing at the center. This is the simplest one to assume, but practically this may not be the case. Okay, but just to do the mathematics, we are assuming this. Okay, we want to keep the maths as easier as possible. Okay, now you tell me under what condition this term becomes 0. This term becomes 0 if I minus k is equal to 0. Correct? Because TB is not 0. TB is a fixed finite value. It cannot be 0. So I minus k is 0 means I is equal to k. Correct? When I is equal to k, I have this is equal to 1. Okay, let me take out that one point where I is equal to k comes inside this summation. So that is equal to, now you see this is when this I becomes equal to k, right? This becomes P of 0, which is 1. So what remains? Amplitude is only mu into ak. Is it okay? So you are taking out the mu into ak. Let me still write the p value here. I'll write it as P of 0 plus, that means you see this summation is all the way from minus infinity to infinity, out of which one term you took it out because its value is known to you, but other values you don't know. So you still write the summation k is equal to minus infinity to plus infinity, but k is not equal to I because k equal to I is already taken. Okay, remaining term you write this is mu into ak into P of I minus k times t. Okay, all right, now let's look at the term. Okay, let's look at the term by term on the right hand side. So there are two terms in the received signal, right? This is the one which is used by the decision making device to decide whether it is 1 or 0. Correct? This is the one. So this equation I need to analyze in detail. Okay. Now there are two terms here. First term is mu into ak. Also, okay, I'll write another term. So since we know that, right, P of 0 is equal to 1, I can rewrite this in the following form. This is the final answer. Y of ITB is equal to mu into ak into 1 plus the same summation. K is minus infinity to plus infinity. K is not equal to I. Rest of the terms, that is mu ak P of I minus k times t. Oh, okay, fine. So that's the answer which we are talking about. Now let us see what are the two different terms present over here in detail. Okay, the first term, right, is nothing but ith transmitted symbol. Are you okay? Okay, so sorry, I'll make one small change just to make it clear. Now, let me rewrite this. So there is a small change I need to make because I am substituting k equal to I here. That's why this is a and this, it's not ak because you substitute k is equal to I, correct? So I made a mistake. So this is actually ai. This is also AI. Are you okay? Because I'm substituting k equal to it, right? Okay, so this is I. In the sense, when you put ith, when you take out ith sample on the receiver side, right, you get one part of your sent symbol, ith sent symbol, correct? First symbol, second symbol, third symbol you send on from input side. When you decode this on the other side, you still get the same thing. This is okay, absolutely fine, right? This is what you need to receive, correct? When you, so I'll repeat my point. When I want to see what was my first symbol, I look at y of 1 into tb. Okay, I is equal to 1. That actually is a scaled version of ai. Ai is a1 because I is equal to 1. Y of 1 is equal to mu times a1. A1 is nothing but your first sent symbol. So no problem, this is absolutely needed for us, right? Definitely it's a scaled version, no problem. I send plus a. This is some maybe mu is equal to, let's say, 0.9. 0.9 into plus a. That's what I get. Otherwise, if it is minus a, you may get 0.9 into minus a. No problem, because plus a was sent, you receive 0.9 times plus a. Minus a was sent, you receive 0.9 into minus a. Absolutely fine. Maybe this will help you in making a decision. Okay, making a proper decision. That's fine. But now let us move to the second term. Right? What is the second term? It says that it is mu into ak into a pulse function where k varies from minus infinity to plus infinity. Okay. Now you see, for ith symbol, right? For receiving an ith symbol, you actually add up all the symbols from minus infinity to plus infinity. Correct? You see the meaning of this. I have, if I am receiving a, let's say a1 is what I am trying to receive, a1. But the a1, right, also get affected by, see, k is equal to minus infinity to infinity will always have a0, right? Because k is 0 is valid, right? A minus 1, a minus 2, a minus 3, correct, and so on. You see, k always varies from minus infinity to plus infinity, correct? That means your current symbol is getting affected by all your past symbols, right? So what do you mean by that? That is the effect of other symbols on your current symbol. Is that point clear? Let me right, if you want me to repeat anything, please let me know, because that's what is a very important point over here, right? Any doubt? No? Fantastic. So which term, first term or second term, which is the ISI here? Second term is what is the ISI. In a most simplest format, we try to understand the ISI over here. Okay, so this is called as ISI. I'll write 1 point below to conclude. Right, so the first term has no issues, absolutely fine. The second term, I'll just write here the second term represents the, I can call it as unwanted, because only the first term is wanted, right? So unwanted, I can write the contribution. This is the unwanted contribution of all other transmitted bits. All the transmitted bits, because why you call it as all, because k is minus infinity to infinity, right? Every other symbol will affect or will contribute to the current symbol. That's what. Okay, transmitted bits on the decision, of the ith bit. So right now, yi of tb is used for making a decision, but this yi of tb has the effect of current symbol, that is mu into ai, plus all the other symbols. So that all the other symbols is what is called as the inter-symbol interference, which needs to be avoided by any means. That's what is our conclusion.